As we look at this example, one of the things that I want to stress to you as you're working through your homework problems, try to make sure we can identify what problems are which. Right? We had this previously with the one sample testing. We had to say, how do we know this is a mean? How do we know this is a proportion? Right? I always encourage you, don't just work through the problems and say, I know it's a proportion because I'm in that section. I know it's a mean because it's in that section. Right? Be able to identify why I know it's what, and it becomes even more important as you move forward. And so your PSA is that on your exam coming up, you will have problems that just ask you to determine what type of test we are working. And I won't actually have you do anything. I just want to know, can you see a setup and do you know what type of test it is? Now you'll have to work some problems out as well. But some of the problems will just be, can you identify what type of problem is what? That's extremely important. So as you go through here, yes, we're in the two sample proportion test, right? But don't just fall back on that. Say, why do I know it's that? Okay. In this example, we've given a whole bunch of patients. We've given some of them Nasonex, we've given some of them placebo, and we have data on what happens there. How do I know this is a proportion problem? First off, I know it's a proportion problem because I have a set number of people who reported something as a quote unquote success out of a set number of people, right? Notice headaches. Uh, Most of us wouldn't call it a success. That's why you might want to use air quotes around it. Because it doesn't really matter what you call success. It's arbitrary. It's just some sort of thing that you can say that's what's counting as my X in the problem. Okay. Um, how do I know it's two sample? Because I'm not comparing how many people in the drug group had a headache to a certain specific number. I'm comparing them to how many in one group compared to how many in the other group, right? So this problem would look very different if I said the patients in the experimental group received Nasonex, and of those 21,000 or 2,100 people, 547 reported headaches, and we want to see, is that different from 25%? If we stop the problem right there, that's a one sample proportion. But by saying, and there was this other sample that had these many people in with this many headaches, now let's compare them. That's two sample, right? So you might want to think to yourself as we move forward, you have a little 2x2 grid. You're going to have means problems and you're going to have proportion problems. You're going to have one sample problems. You're going to have two sample problems. And you have to figure out which of those four quadrants the problem goes into. Okay. So then I set up my alternative, null and alternative hypothesis. I'm going to use the subscripts N and P, N for Nasonex, P for placebo. It's also called the control group. Again, I want to stay away from the C's. If you want to use C here, that's fine. I want to make sure to try to not confuse you. And the question is, again, I'm always interested in the claim, the research question. That direction is the direction that I want the alternative hypothesis to go. So is there significant evidence to conclude that the actual proportion of Nasonex users is greater than control? So that means Nasonex greater than placebo, and so that's why my alternative is P sub N greater than P sub P. Now, you could have written the alternative as P sub P less than P sub N. That's the same idea, and that makes it a left-tailed test, right? So this is a little confusing. So if you need to replay this a couple of times, that's totally fine. What I want to make sure is we understand that however we set up our alternative sets up the order that we do the subtraction in our test statistic. Okay, it's this idea here that whatever you write first, it's that minus the second thing. Okay, so if you put P sub P less than P sub N, when you do your test statistic, you want to do the P hat sub P minus P hat sub N. We are going to do it this way because I wrote them out like English, left to right. Because I wrote this one first and this one second, I do this one minus this one in my test statistic. Because if I do this one minus this one, that should give me a positive number for a right-tailed test. And if I did P sub hat sub P minus P sub hat sub N, that would give me a negative number for a left-tailed test, because in that case, I would have had to flip the sign because it's always that this one's bigger, right? And so just make sure you can work the problem both ways. It's just that when I write this out, I know the order of subtraction in the numerator based off how I've written this out. This is a right-tailed test because I did N minus, just these subscripts, N minus P. Had I done P less than N, I would need to do P minus N. All right, so I know it was a little bit wonky, but just make sure you wrap your brain around that. You can totally work it both ways, whichever way you do it, just you have to stay consistent. Okay. Our assumptions, again, we can do this at the back end, we can do this at the front end, doesn't really matter. Um, no issues with sampling. There's nothing there that says I only had adolescents in one group, or I only had adults in one group, or I only had people from this country in one group, or I only had females or males in one group. There's nothing in there that talks about anything that makes me think I have any demographic issues. I have no reason to think people would lie about this. Um, so there's nothing that jumps out at me as any sort of bias that I would have. So I'm going to say my sampling is okay. Are the groups independent? I would say yes. We have a bunch of people in one group and a bunch of people in the other group, and there's no evidence in the problem that says one would affect the other. Now, this is where we don't want to make something up. There are scenarios where they might be dependent, but something in the problem would need to be written out that says, for some reason, this affects this or something like that, right? Again, we assume there's no issue unless you see it in the problem. So I can say independence works. Do we have binomial distributions? Well, you either are getting headaches or you're not, and you can't both have a headache and not have a headache at the same time, right? We have a fixed number of people in these trials. Like, we didn't keep doing them until we got so many success rates. We have a fixed number of trials. We're going to assume independent. Now we have independence between the trials. We just talked about that, but then we also have independence within the trials. So we not only have to say that the placebo group is independent from the drug group, but we also have to say that within each group is their independence. And again, nothing says that they aren't. It's not like we purposely got a bunch of people together that know each other or something, right? So, or are related to each other. Maybe we did, but the problem doesn't say it, so I'm not going to make something up, right? So we would assume that there's independence within the trials as well, and the probability that you have a headache is the same between all people. No reason to assume otherwise. So we're going to say we have independence and we have binomial distributions, and we have at least 5 successes and failures in both groups. And so that's what leads us to we have normality from both of our statistics. Now, notice I wrote it as a subtraction previously. Now I'm writing it as separate. Either one's fine. They mean the same thing. You don't need to know this, but just as an FYI, if we show that something has a normal distribution and then something else has a normal distribution, when we subtract them, that has a normal distribution as well. You don't need to know why, but it's this idea that as long as I can show they're both normal, then I know that the difference is normal. We're working with the test statistic, that's the difference, so we need to show that's normal, so showing each one's normal works. Okay, so you can kind of write it as we wrote it previously, you can write it as this, it doesn't matter as long as you're either one. And then our test statistic, and like I said, this is super ugly, but just bear with me. If you want to pause right now just to try to give yourself a chance to wrap your brain around the numbers, because they're going to come flying hard and fast through this example here. See if you can get the same answer that I'm going to get. If you're like, I don't know what numbers go where, that's okay. We can go through this and hopefully you can put them all in the right places. I'm working with a lot of fractions here. This would be the proportion of people who had headaches on the Nasonex group. This would be the placebo group. Again, I know what order to do because I'm reading left to right the way I wrote the alternative. Had I done the alternative P sub P less than P sub N, that's when I'd have to flip those. Hopefully that makes sense. And then you would get the exact same answer, but you get a negative. So hopefully you see that if you had flipped the numerator here the other way around, you'd have a negative, which is okay if you have a less than test. If you have a greater than test, you want this positive, so hopefully it should align. And then I got this from combining the numbers. And these are my n's. And so I'm getting a test statistic of 2.84. We have a right-tailed test. And we weren't told a significance level, so we're going to use 0.05 as that, which means my critical value, critical value here will be 1.645. And again, then I can draw in 2.84 goes somewhere over here in the rejection region. Calculate my p-value like we talked about before. It's the exact same way we calculated the p-value previously. Make sure you write our correct probability statement. That's a greater than, so I want to flip it to a less than, go to my table or Excel, and I can get a small p-value, which also means reject. So my answers have aligned. And again, now it's just kind of a downhill lather, rinse, repeat idea. Because our test statistic falls in the rejection region, my p-value is less than alpha, we reject the null. And then my sentence, this is what I said, the sentence is going to get a little bit wordier here, but it's this idea that I still need to come back and write out the alternative in words. I need to have the population word, whether it's actual, real, known population, whatever. I'm going to say that we can conclude that the actual proportion of days and headache users that experience headaches as a side effect is greater than, and now I kind of cheated, right? That of the control group. You can kind of do that if it's the same concept, right? Than that of, of the control group, because we could have also put is greater than the actual proportion of placebo users that experience headache as a side effect. But we already have a lot of words, right? So I kind of just shortcut that from an English standpoint as I wrote that sentence out. And then our second example, again, if you want, go ahead and see if you can work this one on your own. We'll follow up here with the answers. Notice a real easy way to work these two sample problems, or set these two simple problems up is, drug, placebo, left, right, husband, wife, male, female, all these things that have nice easy splits. We know it's a proportion problem because we have we have a fixed number of trials and a certain number of successes, right? What is success here? Success is people who have more than one tattoo. And then we've divvied that up by males and females, and we're comparing two groups to each other, so that's a two sample test. In this one, we don't have a direction, it just says test the claim that they are different. And different just means not equal to. So in this case, it doesn't matter which direction I write. If I write the males first or the females first, does not change anything at all. If I write the males first, I'm going to end up with a positive test statistic. If I write the females first, I'll end up with a negative test statistic. But because it's a two-tail test, it doesn't matter. I have to consider both tails anyway, right? Nothing to report in our sampling methodology. And it seems that we have all of these met again. Now, again, don't just check those off like it's a box. Actually think through these. So I'm assuming that you'll pause and think through them here yourself and just make sure that you can confirm them. That's what you'll be asked to do on the test. There may be cases where they don't work out quite so simple in the test, and they may. You just have to read each question and think through those four binomial characteristics. Each time you have to think through the independence. Is there a reason that the one group would be independent or not from the other group, right? These are just males and females, but what if it's husband and wife? Right? If it's husband and wife, you'd say, I'm not sure those are necessarily independent, right? Because if people know each other, they might, share some viewpoints with each other about how much they like tattoos or don't like tattoos, right? So these are just things we have to check in all the problems. Worked out fine on our two examples here, but may not always. Once we set things up here, once we've identified the problem and set it up, it's pretty downhill from here now. It's just plug and chug. Again, lots of craziness with the test statistic and how we find it. Again, you'll have a calculator or Excel for your own exams and the homework problems to set that up. We have a two-tailed test. We have a 0.1 significance level in this problem, so we're going to use plus and minus 1.645. And our test statistic of 1.37 is somewhere here in the white region, does not fall in the rejection region, so we're assuming we're going to have a relatively large p-value. We know to go greater than because we have a positive test statistic. If you had a negative test statistic, you'd be going less than, right, if you put the females first. You can just be careful with your parentheses here. I want to do 2 times this whole thing, so I want to take this greater than. I want to rewrite this as 1 minus the less than probability, but keep the 2 times outside of that. So if it's 1 minus and then multiply by 2. Look this up in Excel or your table. Subtract from 1, you get 0.0853, multiply that by 2, and now we do get that relatively large p-value. And then just as before, finish up with the same sort of sentences we've been writing. Our test statistic does not fall in the rejection region. Our p-value is large, so we failed to reject the null. And so we cannot conclude the alternative. We cannot conclude that there is a difference between the two populations. We cannot conclude that the real proportion of males with at least one tattoo differs from the real proportion of females with at least one tattoo. And notice again, I'm still putting those same key concepts. I'm still putting the population word, real, proportion is what we're talking about, context of the problem, people with tattoos, and then alternative is differs, right? So I've still got all those same key pieces in that conclusion.